Ladies and gentlemen, we're going to continue our discussion of acid-base chemistry by discussing buffers. So we're supposed to fill in the blanks in this simple activity here, and a buffer must be comprised of it's either a weak or a strong molecule, and then we're going to put an answer here. Any suggestion? So I pick weak or strong for the first one. Weak, it's a good answer. Red looks good. Okay, so two weak things. One has to be a weak. Weak what? Weak midfielder? Base? You want to start with base? Blue. No, I like it. No, it's cool. Weak base and its conjugate. Now you got to say acid. So you need a weak acid and a weak base, and they have to be very important. They have to be related in what way? Conjugate pair, which means they're different by only what? H plus, also known as proton. Nice. Okay, so copy answer X here, base. Base serves to neutralize what? Any added, oh gosh, I almost said the answer. Acid. That's what bases do, right? Yeah, so that the pH does not go. So normally when you add acid to water, the pH goes which direction? Acid? Down, and it goes down precipitously. That just means really fast. So the fact that we have a base neutralizing the acid means the pH is still going to go down, but not very much at all. So down is the operative answer, isn't it? Not go down very much. And what about the other part? Answer Y was acid. Acid serves to, so we got an acid in the buffer, serves to neutralize any added, what? Base. Normally when you add a base, what happens to pH? Goes up. The buffer is going to make sure it doesn't go up very much. We're talking very small changes, very, very little changes. And before we answer the last one, I'm just going to give you an equation we never use, but we conceptualize it and we use it all the time. A very important equation called the Henderson-Hasselbalch equation. It says for any weak acid, if you reorganize the Ka equation, you get this. And it's the concentration of a generic, of the base over the concentration of the conjugate acid. All in parentheses there. And I don't want you to memorize it, but really to conceptualize it, you need to memorize it. Let's go over it again. Bases do what to pH? Up or down? Up. Are you surprised the base is on the top? This is the conjugate base, and this is its conjugate acid partner. Bases raise pH, that's why they're on top. So if this number is bigger than this number, the log will be a positive answer. Now, if the HA, the acid, is greater than the base, this will be a fraction, correct, in the parentheses? And the log of a fraction is a negative number. What's happening to pH if you have a negative number adding to pKa? Where's pH going? Down. Are you surprised? You already knew this. Acids lower pH. But they don't change very much when they're doing a log expression of the ratio of the two. So you can use this equation to answer this next part. The most important thing about buffers is that they keep pH close to what? I'm not going to say what the answer I heard, though, is the most common mistake I've heard on that question for 30 years in a row. No, you both are giving me specific numbers. There are thousands of different buffers that will work at different numbers. So I don't want a number, I want a variable. The variable's already on the screen and the math is there showing that if you have a perfect buffer where you have exactly equal amounts of base and acid, you know the answer to this question. If I have equal amounts of base and acid, what's the ratio? Yes, it's 1. What's the log of 1? 0. What's the pH? It's the answer to the blank. pKa. Now, if you want an even goofier way that I'm trying to emphasize how important this fact is, you go look at the morning video where I say the same thing 3 times and it's there, and I say, next time somebody says that pH will be kept near 7 or 14 or 2, I'm going to say, what was that thing I said 3 times on October 10th, 2022? I said, a buffer, the most important thing about a buffer is that it keeps pH close to pKa. So I will use for an example, a combination of an ammonium ion and its conjugate base, the methylamine. Which one of those is the acid, everybody? You should be able to answer that just by looking at them. Left. What's the pKa of that acid? We have to know it eventually this week. Got a test coming up next Wednesday. 10. You would choose this combination of acid and base. Oh, by the way, does it fit the definition of a buffer? What's the pKb? Is it a weak or a strong base? And I want a number. You should be able to figure it out for me based on what we were doing last week. It's 4, that's right. Strong or weak? Weak. Weak base, acid, strong or weak? The methylammonium ion on the left. It's weak? Yes, it fits what's on top of the screen. You have to have weak of each. Now, I didn't explain in the morning video why it had to be weak versions of each. I will explain it now. If you try to make a buffer from something like hydrochloric acid and its conjugate base, which is what? The conjugate base of hydrochloric acid, what's its name? I want its name. Let's say chlorine. What's the conjugate base of HCl called? Don't say chlorine. You might have been saying it. You're too far away. I can't. What do you get when you take a proton away from HCl? No, you do not get Cl. Cl minus. What's its name? Chloride. Okay. Anyway, that's 141 review there. Don't worry too much about that. Okay. The reason why HCl and Cl minus, that pair, is not a good buffer, it's not HCl's fault, even though HCl doesn't fit our definition of you need to have a, let's see, a buffer must be a weak base and a conjugate acid, which is weak, but HCl is not weak, right? It's -5 the pKa. It's even lower if you want to know the real number. That's not the reason why it's a bad buffer. HCl is great at neutralizing base. Nobody's better than HCl. But Cl minus can't neutralize any acid. It's too weak. So if one of the partners is strong, it means the other guy's too weak to help out in the neutralization department. It won't be neutralizing anything. It can't react. It's sitting there. Cl minus is a spectator. I can't take an H. I have no desire to take an H. This is how I'm doing my Cl impersonation, chloride impersonation. Not interested in picking up a proton. So that's the real reason why this definition exists. It's a little misleading because the definition's worded like it's got to be a weak base. It doesn't have to be. It could be a strong base. Strong base neutralizes acid, but its conjugate acid partner can't neutralize jack. Okay? Nothing. It neutralizes nothing. So there you go. I think that this video with the morning video, which had a lot of words, but good words, will give you a real good sense of the importance of buffers, because we got into proteins this morning and how protein shape is everything for proteins. You might not know that, but you should know it now. When we get to proteins in this course and in your biology courses, it's all about the shape. Shape is maintained by things like hydrogen bonding. Hydrogen bonding is changed if your pH changes, because you're throwing protons in there, right? Or taking protons away. That's going to change the shape of your molecule. You better have buffers around to stop that pH from changing. Okay? All right, so we got that. So that's the end of this video. You just fill in the blanks.